When a high-performance processor is overwhelmed by chaotic internal interference, it loses the capacity to process data. It goes blind, overwhelmed by its own noise. Classical medicine frequently observes this state in chronic neuroinflammatory conditions like severe autism or PANS. The standard clinical conclusion is that the erratic outputs and communication breakdowns are the result of static, unrepairable hardware damage. Systems engineering proposes a distinct counterargument. The biological hardware is completely intact. The processor is not broken, it is suffering from catastrophic signal saturation. This split screen visualizes the mechanical failure. On the left, an elevated baseline noise floor runs rampant. On the right, we see the consequence on the oscilloscope. Incoming environmental signals hit the hardware's voltage ceiling. The data is aggressively flattened and clipped at the top and bottom. Nuanced data like speech sounds like painful, distorted static. Treating a functional signal jamming issue as if it were a permanent structural defect guarantees clinical failure. You cannot rehabilitate a circuit by ignoring the noise floor that is actively suppressing its logic gates. The primary clinical proof that these logic gates are jammed rather than destroyed is known as the zolpidem paradox. Zolpidem is a standard sedative. When administered to specific saturated patients, it acts as a metabolic signal pad. It artificially lowers the internal excitatory noise and increases the system's inhibitory gain. The immediate consequence is profound. As the noise floor drops, the underlying signals for consciousness, speech, and motor control emerge. The sedative does not generate new brain power or repair physical tissue. It simply removes the static. Neuro-Recovery engineering is a framework designed to permanently replicate this exact drop in the noise floor, restoring the necessary voltage headroom without relying on pharmaceutical sedatives. If complex consciousness can emerge instantly under the right metabolic conditions, the engineering objective shifts. We do not need to build a new processor. We need to clear the biological static hiding the original one. When a processor is completely saturated by internal noise, it becomes effectively blind to environmental data. To regain spatial or sensory awareness, the hardware must deploy extreme survival tactics. This diagram illustrates a principle called stochastic resonance. We start with a weak sine wave buried in a chaotic noise floor. By injecting predictable white noise into the circuit, we mathematically boost the peaks of that weak signal just above the detection threshold, allowing the system to read it. When a child engages in repetitive motor actions, like rocking, humming, or hand flapping, they are not misbehaving. They are manually executing this mathematical process. The hardware is injecting a predictable physical rhythm to boost underlying sensory signals above the static. While stimming is a bottom-up physical workaround generated by the body, an engineer can employ a top-down control override, known as the vagal interrupt. Using cold water physical pings, we send an emergency brake command up the vagus nerve to break the system's defensive posture. This produces a calm state within a 90-second recovery window. A paradoxical spike indicates communication jitter and an underlying grounding failure. There is a precise operational difference here. The biological hardware hacks its own noise floor through repetitive motion. The engineer actively overrides the logic gates to test the brakes and force a systemic reset. You cannot stabilize a high-performance processor if its power supply is leaking dirty current. This network map isolates the gastrointestinal barrier as the body's logistics hub.
It is connected directly to the CPU triad in the brain via the vagus nerve, which acts as the main bus cable. Pathogenic biofilm scaling and inflammatory dietary triggers inside this hub create significant biological impedance. This impedance bleeds dirty current directly up the main bus. It acts as a parasitic drain, artificially elevating the brain's baseline thermal noise and pushing the system closer to its voltage ceiling. The strict prerequisite for recovery is sealing this logistics hub. Establishing strict input controls unprimes the circuit, reduces the continuous influx of inflammatory data, and restores baseline voltage headroom. Skipping this infrastructure repair renders all downstream neurological therapies useless. Any neural shields deployed at the processor level will simply be bypassed by the continuous static radiating from the gut. Once the logistics hub is verified as secure, the engineer deploys the technical stack to address the hardware's locked defensive posture. These vacuum circuit breaker diagrams illustrate the hysteresis latch. After an impulse event lacking damping capacity, the system permanently latches into a high-alert attack state. We break this latch not with massive pharmacological force, but by nudging the latch with precise, low-voltage supplement signals. By introducing micropulses of compounds like inositol and NAC, we are effectively vibrating the mechanical latch. We supply a steady sequence of cooling and grounding signals to coax the microglia into initiating a logic reset. The engineer then monitors a strict 12 to 48-hour telemetry, such as spontaneous speech or steady eye contact. These precise micronudges leverage the system's native drive toward homeostasis. We supply the exact metabolic hardware ping required, and the body does the rest. If the micropulses fail to produce a result, the engineer encounters a zero-delta scenario. The system remains stalled in a latched state, entirely overwhelmed by existing interference. This requires moving to the active flush protocol, a necessary, high-risk industrial debridement of the biological interference clogging the system. We use targeted antimicrobials to forcefully strip away accumulated biofilm scaling and clear the pathogenic buildup, acting as a continuous source of static. The immediate risk of this fluid dynamic sweep is a Herxheimer event. As pathogens are destroyed, they release high-energy debris, causing a transient spike in the systemic noise floor. An active flush must be tightly governed by real-time diagnostic trouble codes. This telemetry overlay tracks markers like vagus bus jitter. If the system logs a paradoxical spike, we deploy a technical patch, increasing the glycine ground. You don't discipline the hardware for failing. You adjust the circuit to handle the load. Strict adherence to real-time telemetry separates precise, data-driven system management from reactive medical guesswork. We map the inputs directly to the observed outputs. The ultimate engineering objective is laminar flow. This is a state where the hardware possesses enough voltage headroom to process the external environment without clipping, stalling, or causing pain. This graph demonstrates the biological result. As the turbulent noise floor drops below the switching threshold, the flattened waveforms smooth out. The data stops clipping. With the alarm deactivated, microglial drones resume synaptic pruning, clearing away redundant, noisy data paths. This leads to the final phase of the protocol, the fade-out principle. Success is not measured by long-term compliance to a massive permanent supplement stack. The technical stack is a temporary scaffold, used to enforce stability. Once dynamic homeostasis is achieved, the external controls are slowly dialed back. The metabolic heat sinks and signal pads are removed as the body's autonomous self-regulation takes over. Neuro-recovery engineering proves a vital reality. You aren't building a new child. You are simply clearing the systemic static, so the original, completely intact system can finally run its native code.